In classical mechanics, if a force is applied over a distance, work is being done, or energy is being transferred, from the object doing the work to the object that the work is done upon. By energy here, I mean kinetic energy, that is, the energy of motion, which is described by this equation. Contrasted to kinetic energy, there is potential energy. Potential energy comes in many different forms: gravitational, elastic, chemical, but generally it is the stored energy of an object based upon its relative position to other objects. To understand the relationship between kinetic and potential energy, imagine a ball standing still on a flat ground. For our purposes, we could say that it neither has any potential nor kinetic energy. Now imagine the same ball standing on top of a high hill. In this case, we could say that it has high gravitational potential energy, but still no kinetic energy. If the ball is somehow then taken out of equilibrium, all of this potential energy will be converted into kinetic energy as the ball rolls down the hill. Now, instead of imagining a single ball, imagine a collection of balls, swirling around in a closed system. Because the system is closed, the sum of the kinetic and potential energies of all these balls won't change. It will just be able to convert between the two as the balls bounce from one another. If the system is open, however, new energy can enter in, but it has to be lost from another system somewhere else. Energy can also get out, but it has to go somewhere into another system. And see, you soon discover that energy cannot be created nor destroyed. It can only be converted from one form to another. This is known as the first law of thermodynamics, the branch of physics that deals with energy, and is the reason why me, you, and all life on the planet stays alive. As the balls keep hitting each other, the sum of their kinetic energies, called the thermal energy of the system, will eventually diffuse and end up being evenly distributed all around it. This is the second law of thermodynamics, and what it really states is that the entropy of any closed system will always tend to increase. You can think of entropy as a measure of disorder, sameness, or homogeneity of a system. Now, what I've said so far has been primarily about classical mechanics. In quantum and relativistic mechanics, light can be thought of as pure energy because it has no mass and its velocity is constant in a vacuum. The energy of light is described by the following equation. Although it has no mass, light can bundle up upon itself and be confined to a small region of space. This region now, which you can think of as a particle, will exhibit the property of mass, the measure of which will be proportional to the energy of the light. The same idea can be applied to particles which already have mass, and the effect can compound into even heavier particles. And because we usually define matter in terms of mass, matter is really equivalent to energy. And with that all said, let the Big Bang bang. Space, time, and all the matter and energy within it begin to evolve, and the second law takes a hold as the universe slowly begins to diffuse and disintegrate. Now is a good time to mention the tendency of matter to fall towards higher stability, that is, a lower energy state. This is also because of the second law. When there is a drop in energy, like in the case of an electron in an atom falling toward a lower shell, to retain conservation the energy is given off in the form of a photon. Eventually, all matter falls towards the stable structure called the hydrogen atom. As enormous amounts of these atoms curve space-time and cause gravity to pull things together, hydrogen stars form. Within these stars, a process called nuclear fusion occurs. This is where, due to high temperature, electrons become delocalized from the atoms, and due to high pressure, the nucleus is fused to form heavier elements like helium. Because there is a big lowering of energy, stars give off high-frequency gamma-ray photons. Some of these stars tend to become supernovas and explode, and some of the new elements made within them are also pulled together by gravity and into the orbit of a new star to become planets. Some of these planets may come to have water on them, like our Earth, in which great amounts of thermochemical evolution can occur, due to water being the universal solvent. The only source of energy that the Earth receives is the light from the sun, which forms energy gradients in the water as it flows from hot to cold. Such gradients also form deep underwater due to the geothermal energy from the Earth's core. In these, something very interesting happens. Large macromolecular systems form that are able to lower their internal entropy so to increase the entropy of their surroundings. They are in a sense converting received energy through themselves only to better disperse it into their environment as heat. The second law is not violated because these systems are open. In classical information theory, entropy is defined as being inversely proportional to information, so as entropy decreases, information increases. Complexity emerges. Eventually, these systems may have developed a mechanism for self-replication because of the extreme efficiency of self-replicating systems to dissipate energy. And when you have self-replication, you have life. To understand life, imagine a single replicator, a molecule able to pick up pieces of itself, build itself, and then separate from its copy. Soon, a population of these replicators is going to form. Mistakes can happen in this copying process, and here is where natural selection takes a hold. Mistakes that lead a replicator replicating faster or more accurately are gonna lead it to present a larger portion of the population. We can now call these replicators organisms. An organism is really a machine that through metabolism, a string of chemical reactions, is able to use the energy in the environment to make more of itself, but also to sustain homeostasis, that is, the internal workings of its system. Retaining homeostasis longer means living longer. Traits for living longer or surviving are also gonna be selected because they lead the organism to replicate longer. The first organisms were the prokaryotic and then eukaryotic cells, with which evolved the two primary energy conversion mechanisms found in living systems: photosynthesis and respiration. Photosynthesis is a process that a cell does which uses the energy of light to initiate a chemical reaction between water and carbon dioxide found in the environment that takes the carbon in and releases the oxygen back out. The cell then uses the carbon to grow and make more of itself. Respiration is the same reaction in reverse, meaning a cell takes the oxygen in the environment and combines it with its carbon to release or use energy. Now, not all cells were able to do both photosynthesis and respiration. Some had only respiration. They evolved to consume other organisms to get their carbon. These will come up to be the animals, and the ones that did both will come up to be the plants. It isn't very difficult to see why the animals had to be more efficient in interfacing with their environment, so they developed nervous tissue, which in the beginning had the ability to perform only direct input-output operations, but as time passed, a bundle of this tissue formed called the brain. This brain was now able to delay the input from the output and create some sort of a memory. Then, based on this memory, it could make predictions about the future. An internal simulation of time or consciousness had formed. Now, animals were able to sense and actuate. The actuation of some animal's behavior could become the sensation of another animal. In this way, behaviors, which by the way were also bound to meanings, were in a sense replicating within the intersubjective reality of animal communities. In certain primates, this evolved so rapidly and resulted in the familiar notions of culture and language. These primates, which we can now call humans, gained a tool to organize an economy. How's that relevant to us? It's relevant because although all species use energy on the individual level, through an economy, a species uses energy as a collective. One of the first type of economies is the primitive hunter-gatherer's economy, which was organized around the collection of food. But food wasn't the only use of energy back then. Combustion is an exothermic reaction between oxygen and a fuel, the fuel being anything like wood, sticks, or really any organic matter that burns. During a combustion reaction, the chemical potential energy stored within the bonds of the fuel's molecules is converted into thermal energy or heat as the atoms break free from these bonds. And due to a drop in the energy states, the reaction also produces light. So really, the hunter-gatherer's economy supplied energy in the form of food along with heat and light. even combining them as heat was used to cook the food, leaving our stomachs to do less of the work. Some time passed and little by little, land, crops, animals, or really portions of the biosphere were getting domesticated by us humans, allowing us to settle and build infrastructure around these portions. And these came with its own downsides, but having agriculture meant having a surplus of energy, which led us to spend more time improving this new system by inventing new agricultural tools and simple mechanical devices, like the wedge, the inclined plane, the wheel, and the lever. What these devices really are is a way of converting mechanical energy to control the direction and magnitudes of force vectors and do useful work. It's going to be more than 2000 years before a formalized view of how this works appeared. But when it did appear, it got us this. The steam engine is the main prime mover that's responsible for industrialization. Before the steam engine, previous prime movers were either powered by human or animal labor or by the Earth's cycles, like watermills and windmills, which take the kinetic energy of Earth's moving fluids and convert it into rotational motion. The steam engine, on the other hand, uses the thermal energy produced in a combustion reaction to turn water into vapor. The vapor then pushes propeller-like blades or pistons to create motion. The problem with this, however, is that burning sticks cannot produce the energy needed to do the work. So we began using fossil fuels. A fossil fuel is any organic matter that has been buried underground through the centuries of evolution and has been exposed to very high temperatures and pressures. This makes it very dense, therefore it has a lot of energy stored. Fossil fuels come in a solid state as coal, liquid as oil, and gas as natural gas. Steam engines were first used in mines and factories for all sorts of machines, and then to power new modes of transportation, like locomotives and steamboats. This caused economies around the world to expand and connect. But there was another problem. With just a steam engine, you could power things only locally. You cannot go far translating the energy with just gears. For that, you need wires. A wire is a string of conductive material. A conductive material is one in which the outermost electrons of the atoms composing it are few enough so to be able to move freely. These electrons have a property called electric charge. If you make them move, you generate an electrical current, and the kinetic energy of the now moving charges, called electrical energy, can be used to do work. In 1831, Michael Faraday discovered that if you pass a changing current through a wire, a magnetic field will form around the wire, and if you wrap the wire around a coil, the magnetic field will be generated around the coil. Now, this works both ways. If you pass a changing magnetic field through a wire, you will induce in it a current. What if we use this with a prime mover that generates some rotational motion? By putting a permanent magnet to be rotated and let it be surrounded by conductive coils. As the magnet rotates, it will generate electricity. And the same process in reverse could be used to power an electric motor. Other things we could do with electricity is turn it into heat or light. The way this is done is by strategically placing a resistive material in the path of the electrical current, so the electrons smash into the material and make its atoms jiggle, which produces heat. The electrons of the material, on the other hand, could get excited into a higher energy state, so when they fall, photons are emitted, which produces light. All of these new capabilities are employed as a new grid infrastructure is built to distribute electrical energy from power stations to our entire civilization. Many more developments occurred during this progression, like the invention of the battery, which stores electrical energy as chemical potential energy to be used later when needed. The use of the thermal energy produced in nuclear fission, which is the splitting of heavy nuclei into lighter one, and the construction of nuclear power plants. The switching from coal to oil as a primary fossil fuel, the invention of the automobile and the internal combustion engine, and yeah, as you can see, things are accelerating. And this acceleration gets us to the present day. Regarding energy, the 21st century is primarily occupied with renewables. Why? Because 80% of our total energy comes from fossil fuels. And fossil fuels? Well, First, they are unrenewable, meaning we're gonna run out of them eventually. And second, the combustion reaction releases negative CO2 emissions that are harmful to the environment. So, what are the alternatives then? Well, I mentioned wind and hydropower, and we have progressed a lot since the pre-industrial windmills and water mills, with things like solid-state wind energy only recently coming into view. Another source is geothermal energy. This is primarily used to power and heat buildings from right beneath them. There is also nuclear fusion, which we are yet to harness due to the high temperatures and pressures needed. Providing energy from nuclear fusion is actually one of the 14 grand engineering challenges of the 21st century. But wait, wasn't the sun in a sense already a giant fusion reactor? Yes, and this gets us to solar. Solar power is provided through silicon-made solar cells, which take advantage of the photovoltaic effect, due to which high-energy photons can break electrons out of their bonds. The electrons that are broken from the silicon are then transported through something called a p-n junction and captured to do work. Making solar power economical is also one of the 14 grand engineering challenges. But how do we make this, not just for solar, but for renewables as a whole? Donald Southway, the inventor of liquid metal batteries, says that the missing link in renewables is the efficient storage of energy. This is because you can use a previously stored surplus when you have a current deficit in production. Efficient transportation is also needed. The reason is that one geographical location is going to be better at producing one type of energy than another. So different regions need to be good at transporting and trading energy between one another. There are also smart grids. Grids that first are able to process data from the environment, take into account different logistics, communicate with themselves at all relevant points through IoT or the Internet of Things, and then use machine learning algorithms to learn to adjust themselves accordingly. Combine all of this with the switching from fossil-fueled vehicles to electrically powered vehicles, and a greener future is waiting ahead of us. Will we one day become a solar-punk civilization that's able to convert all of the energy received from the sun to be used by its citizens the same way plants do for their cells? Perhaps a civilization that's able to use all of the available energy on its planet? A Type 1 civilization? What would we even do with this energy? I know what I would. Plug a charger into a receptacle, the other end into my phone, turn on the phone, and watch a YouTube video. Thanks for watching.